Hey everybody. Today we're getting into Maclaurin series. A Maclaurin series is just a Taylor series centered at 0. Here's the formula. Maclaurin series are the most common sort of Taylor series. They're also the easiest to calculate. Here's a simple example. f of x equals e to the x. This is simple because all of the derivatives are just e to the x. And when we plug in 0, therefore, we always get 1. So the Maclaurin series for e to the x is just the sum of 1 over n factorial x to the n. If you do the ratio test on this, you'll see that the interval of convergence is all real numbers. The radius of convergence is infinity. We'll do ratio tests to determine intervals of convergence on the other examples in this video, so we'll skip it on this one. Example 2. Find the Maclaurin series for f of x equals cosine x. So we need to get as many derivatives of this function as possible. The first derivative is negative sine of x. The second is negative cosine of x. The third is positive sine of x. The fourth is positive cosine x. And then we start getting repetition. That pattern's just going to repeat itself. So the derivatives at 0 are going to go 1, 0, negative 1, 0, 1, 0, and so on. Summarizing that, the nth derivative at 0 is going to be 1 when n is 0, 4, 8, and so on, because the pattern repeats every 4 derivatives. It's going to be negative 1 when n is 2, 6, 10, and so on. And it's going to be 0 if n is odd, so otherwise. Okay, given that we know this, we can write out as many terms of the series as we like, just by plugging in. The coefficient c sub n is always going to be this nth derivative at 0 divided by n factorial. So here are the first few terms. Now, even just seeing those first few terms, I can already come up with a pattern and write the general formula for the Maclaurin series of cosine x. It's the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. The negative 1 to the n gives me the alternating series, and the x to the 2n gives me only the even powers of x. And of course, the 2n factorial in the denominator ensures that my factorials always end with even numbers as well. Let's talk about the interval of convergence on this one. Of course, we're going to use a ratio test. We're going to take the limit as n goes to infinity of adjacent terms in the series. The absolute value will immediately kill the negative 1s, so I'm just going to leave those out. Now I'm going to do the division by multiplying by a reciprocal. I'm leaving the absolute value out entirely here because the exponents on the x's are always even. And of course those factorials are always going to be positive. Now there's a lot of cancellation. All I'm left with is the limit as n goes to infinity of x squared over 2n plus 1 times 2n plus 2. So for any number x, the denominator is going to go to infinity, the numerator's not, so whatever x is, this is going to 0. The ratio test says that the series will converge if this limit is less than 1. It's always less than 1, so this series always converges. Converges for all values of x. Now, it's tempting to always do a Maclaurin series when you need a power series for some function. However, doing lots of derivatives and evaluating them at 0 is potentially a lot of work. It can be really hard. So you should use your general knowledge of power series to look for shortcuts. Let's do a couple examples showing that. Find the Maclaurin series for f of x equals x squared cosine 4x. If we just plunge right in and start doing derivatives of this, we're going to start suffering because we're going to have product rules at every step. And every time we do another derivative, that product rule is just going to get a little bit more complicated. Instead, let's use the fact that we know the Maclaurin series for cosine of x already. Here it is. Let's take out x and replace it with 4x and simplify that a little bit. So this is the Maclaurin series for cosine of 4x. Now I want to multiply by x squared. That means on the right-hand side, increasing the power of x by 2, hence the x to the 2n plus 2. There's the Maclaurin series for x squared cosine of 4x, with almost no work whatsoever. the radius of convergence here is still going to be infinity. One more example. Find the Maclaurin series for f of x equals the natural log of 1 plus x squared. There's lots of different ways to do this. However, just taking lots of derivatives, plugging in 0, and computing Maclaurin series coefficients directly is probably the hardest way to go. After the first derivative, you get 2x over 1 plus x squared. And so future derivatives are all going to involve quotient rules. It's going to get painful fast. So one simple shortcut is to find a Maclaurin series for the natural log of 1 plus x. Now my derivatives are going to be nice and simple. The idea is that once I do that, I'm going to take out x in that series and plug in x squared to get the Maclaurin series for ln of 1 plus x squared. Okay, so let's get some derivatives for this new function, ln of 1 plus x. I get 1 plus x to the negative 1, differentiating that, negative 1 plus x to the negative second, and so on. Plugging in 0, I get 0, 1, negative 1, 2, negative 6, and so on. So the signs are alternating, and each time they are growing by a factor of, it looks like n or n minus 1, depending on how you're counting them. So when I actually go ahead and compute my Maclaurin coefficients, I'm going to be dividing by n factorial, so I'm going to get some cancellations there. Overall, the nth Maclaurin coefficient is going to be negative 1 to the n minus 1 over n. So here's my series for the natural log of 1 plus x. X minus 1 half x squared plus 1/3 x cubed, and so on. Taking out x, replacing it with x squared, I'm going to be able to get the Maclaurin series for the natural log of 1 plus x squared. X squared minus 1 half x to the 4th plus 1/3 x to the 6th, and so on. Let's check the interval of convergence. We take the limit as n goes to infinity of the ratio of adjacent terms in absolute value. Do some cancellation to get the limit as n goes to infinity of the absolute value of nx squared over n plus 1. The n over n plus 1 is just going to 1, so of course I'm getting x squared. The ratio test says that the series will converge when this is less than 1, and therefore this series has a radius of convergence of exactly 1.